time lah, actually. You're busy for other subject. So I prefer you all to listen during the online class lah, live class lah. So the recording serve as a purpose, or maybe you want to recall back lah what have been discussed in the class. Okay. Right. So before I forgot another one, we will take attendance using camera attendance. We take the camera attendance. So I will inform lah everyone when the time to take the attendance. So get ready lah. Okay. This is the CO of the course. Okay. What is CO? Cost outcome. Cost outcome, I think all of you already familiar. Actually, what is actually the target lah? Okay, by the end of this course, mean week 14 though, you all should have the ability of the three, okay, which is number one, ability to analyze, okay, analyze by applying necessary knowledge, okay, to analyze behavior of sequential design. You look at the keyword here, sequential design. So we will focus more on sequential design, okay. So this actually reflect to PO, program outcome. So program outcome actually referring to the electronic engineering program, okay, PO number one, which is on knowledge, okay, knowledge on fundamental knowledge on natural sciences, mathematics, okay, okay. So we will apply it to CO number one, especially on sequential design. And then ability to design, okay, analyze circuits, characterization, and overall performance of VLSI design. So PO number three, if I'm not mistaken, is more on design lah. Okay, design. Okay, the design not only using the very long HDL to do a coding. Design maybe we look into the design parameters. Design parameters, for example, area, speed, performance. Just now, that's actually the target. So what are the design parameters to achieve the target? Reduce the area, reduce the power consumption, and increase the speed performance of a design. Okay. And the last CO, okay, ability to engage and conclude the technological change pertaining to VLSI design. So this CO actually will focus more on the ability of the student to explore on their own lah. Okay. Maybe you go online, okay, get a journal paper, a conference paper, do a reading, and then explore, okay, in the scope of VLSI design, okay, right? So to look into the current technology lah on the VLSI design. So this normally available inside the journal or the conference paper, okay. So normally we cover this in the assignment lah, So this very important to look at lah. Okay, final exam. How much final exam? 60%. Okay, 60% is very important lah. Okay, you know right? Everyone know right? When you pass your final exam, you pass the subject. If you not pass the final exam, you need to repeat the subject, right? Am I right?
Yes.
Yes, sir.
Yes, sir.
Yeah, so please be careful on this one. So final exam is very important. I'm not saying the continuous assessment is not important. Both are important, but final exam is actually a key for you to pass the subject. To pass the subject, yeah, exactly. Okay. So please do your very best lah. Okay. I know you all can do it. So we have 2 lab only. Only 2 lab. Okay. Lab number 1, RTL simulation, logic synthesis and analysis. So you will be given a task. Okay. So normally a student group of 2 or group of 3. Okay. Or maybe group of 4. I will decide later lah. Okay. So within the group, the student will do the lab. Okay. Each of the group will have different tasks. Okay. Maybe if group number 1 will do task on multiplier, for example. Group number 2 do tasks on adder, for example. Group number 3 on chart structure. Group number 4 maybe multiplier and so on. Okay, so you will have different tasks for each of the group, and then you will do your lab using the synopsis, as I mentioned just now. Okay, lab number 1 and lab number 2 is actually as a continuity lah. Okay, lab number 2 continuation from lab number 1. Okay, normally we allocate 2 lab session. Okay, means that maybe within 2 weeks is allocated for lab number 1. The first week for you to explore, to familiarize with your new software. Okay, and then you do the lab number 1 as well. Okay, and after that, lab number 2, you will continue lab number 1, but you will do the automatic place and route. Okay, different tasks lah. Same design but different tasks. So lab number 1, you do RTL simulation to make sure your design, for example, an adder is working as adder as expected. Okay, 2 plus 3 become 5, for example. Okay, so you will verify using RTL simulation. You will see the waveform. Okay, using the synopsis. So for digital IC design, we use quarters 2. But for this subject, we use synopsis. Okay, you can also use the quarters to double check lah, but it's not compulsory lah. It's actually extra effort from the student. We will use synopsis software to do the RTL simulation. And then you will do logic synthesis. What is logic synthesis? Favorite question normally asked in exam, either test or final exam. What is actually logic synthesis? Any of you boleh jawab? Can answer. This keyword also okay. Don't worry to make a mistake. Don't worry. What is logic synthesis? What is logic? What is logic? Paling mudah. What is logic? Or what is synthesis lah? Any you can define. You can use a chat box if you cannot use a microphone or you feel not comfortable to answer using a voice. You can also reply in the chat box. Okay. Maybe I will use after this. I will use different apps lah, so that everyone can respond and can see. I may mention each synthesis combine all the logic circuit. Synthesize, combine all the logic circuit. Okay, about to. Okay, any other try? The process of automatic production of logic component, in particular digital circuits. Process of automatic. The words automatic itu acceptable, but the rest, okay. So lab Maribah, our lab we will do on week 3. Week 3 or week 4 lah. Let's everyone settle down first. You understand the course first, understand the lecture first, and then we will do the lab. I will give you time lah actually. Okay, we'll make everyone happy lah for this subject. Inshallah, will do my very best lah. Okay, when you learn the subject, I believe you will digest it lah, and then you can use it for the other subject. Because we have another subject, okay, on the 4th year, we call a system on chip. So that subject is actually continuation of this subject. Okay, so you will use the same software, synopsis, but you will do bigger design, system-based design on the system on chip subject. So please don't simply drop this subject lah, because if you drop this subject without concrete reason, okay, you might suffer lah in system on chip subject. So that's my suggestion lah. Ibnu Qayyim mentioned Suharan mentioned gate abstraction of gate level lah. Gate that's good point. Okay, but not complete yet. Okay, good. Gate abstraction of gate level. Okay, gate level. Okay. Process of transfer. Ibnu Qayyim mentioned process of transfer right A high level like RTL. Level, okay. RTL higher level compared to the gate level. Okay, gate level is lower level than the RTL. Okay, RTL is at the register. Register ni like a flip flop. Okay, register transfer level. Multiplexer, ALU, that's actually register transfer level. Gate level means that lower level than that. Means that, for example, you designing an adder. An adder comprises of several number of gate, right? Or gate, and gate. So that's actually gate level. Okay, the adder is RTL level. Okay, kami ini mention an abstract specification of desired circuit. Typically, a register level is turned into a design implementation in terms of logic gate, typically by computer program called. Okay. Other point, we can see the point. Okay, where you get this one, Kamini? Is that from internet or you write your own? Both okay to me as long as you understand. Good. Okay. Internet, okay, good. Also good. Okay. Normally, the learning process is not actually like 10 or 20 years ago when I was a student. The learning process right now is very, very diverse. Okay, you can get information from anywhere, but you need to cross-check with the textbooks and also with the lecture. Okay, good. Okay, process of I mentioned process that abstract specification of circuit behavior. Abstract, okay. Circuit behavior also okay, but we need a complete one. Okay, good. Okay. Process of transforming HDL design into a gate level. Okay, Anita. Okay, ni kalau face to face lah boleh bagi hadiah. I can give you present lah ni. Process of transforming HDL design or HDL code into a lower level. Okay. Yes, correct. Gate level. Okay. Nurul mentioned same as Anita, process of converting high level description. Yeah, correct. Because HDL code, HDL can be very long, or VHDL. When people mention HDL, it can be very long, or VHDL. Okay. Process of converting high level description, so in this case, HDL, of design into an optimized gate level representation. Okay, good. Where you get this one, Amirul and Anita? I think you get somewhere else. Okay, good. Okay, hopefully you all can digest this one. Logic synthesis is a process by which an abstract form of desired circuit behavior, typically register or behavior, is turned into design implementation in terms of logic. Okay, yeah, okay, good. Okay, thank you. Good response from everyone. Right, so correct. So that's actually synthesis. Basic words of synthesis. Actually, we translate. Okay, we translate from higher level of design abstraction or high level description into a lower level into lower level, like gate level description. Okay, why we mention gate? Because we have logic gate. We also have a lower level than the gate level actually. Okay, which is transistor level. Okay, transistor level. Transistor level, you know, two types of transistor, PMOS and NMOS transistor for CMOS design. So that's actually the very lower level. For example, an inverter. Okay, an inverter is actually not gate, gate top. Gate top in Malay we call gate top. Not gate means that you have input 1, you get output 0. Or the other way around, you have input 0, you get output 1. The inverter. So the NOT gate or the inverter gate is actually comprises of 2 gates. Okay, PMOS and NMOS. Okay, that's for CMOS design. Okay, so at the higher level of abstraction, you write in the coding a sign, okay, A equal to inverted B, for example. So that's actually very long. Yeah, higher level. Lower level, at logic level, you have the symbol of the NOT gate. Even lower level, you have the transistor that form that NOT gate. Okay, clear? Okay, sir, macam mana nak tahu that? Okay, don't worry. I will create the actually the as usual lah. I will create the Google form later on. Okay, I will see the number or actual number of students first lah, and then I will decide either group of 2 or 3 or 4. Okay, and also the resources in the lab as well lah. As we mentioned that we have about 10 software license, so 10 licenses. So we will see lah whether we can have in the time under the timetable we have 4 session. So please block lah that 4 session for other subject to avoid clash lah with other subject. We try to give access to every one of you to use that software. Okay, so that you have the chance to use it. Okay. Okay, thank you for the response. Okay, so the textbook, okay, this is actually the textbook that you may refer. Okay, the textbook, you can get it available. I believe it's available online. You just Google it. Okay, CMOS VLSI design. The type is CMOS VLSI design. Okay, I type inside this box lah. Okay, CMOS VLSI design. The author is Westy. Okay, you will see the book. Download that book. Okay, that book is a older version of book, but the content is still the same. Okay, right. So not all the chapters inside the book will be covered for this course. However, I think that's actually the main reference book lah, or the textbook lah. Okay, please read that book. Okay, because for this subject you need to have to understand the theory to score the subject. To understand the theory, actually there is no shortcut lah. You need to read and digest what is actually inside the textbook and discuss in the classroom. Okay, the reference number 2, number 3, number 4, number 5 ni, you may refer it when you feel that the textbook is not enough information to make you understand. Okay, you may refer it. Okay, strongly suggest lah. Okay, okay, but the main reference or textbook here you have to have it. Okay, to understand the subject. Okay, so this week normally we target to cover this one lah, introduction to VLSI design. Okay. Any question before we proceed? Ada soalan? No question, huh? So you managed to get the book, huh? You type CMOS VLSI design, will stay. You will see the book. Huh? Okay, so in terms of syllabus, okay, this is just a plan lah. Okay, we try to cover as much as possible. Okay, for example, maybe week number 2 element, maybe we can cover in week number 1, for example, or maybe week number 2 cover in week number 3, depending on the pace of the student lah, performance. Okay, and the response in the class. If you all understand, we can make it faster. So actually, introduction to IC design, VLSI design, and then we will look into the VLSI design methodology. So how the chip being designed, okay, and sequential circuit design. As I mentioned to you, this is CO number 1, sequential circuit design. Sequential circuit design. Sequential design. Okay, very important. Okay, so we allocate 1 week to cover this, or 2 weeks, sorry, 2 weeks to cover this, because this is the main target for this subject. The student should have an ability to understand and also apply what we call here, apply, analyze and apply necessary knowledge to analyze behavior of a sequential design. So 2 weeks we allocate for it. And then you will go to the clock design. how do we design a clock? Okay, how do we design a clock? And then 2 week as well. And then week number 7, before you go for mid-semester break, because this is semester break after week 7, you will explore on the interconnection inside the deep submicron. DSM stand for deep submicron, or easily we mention that in chip interconnect lah. Okay, how do we interconnect block in the chip? Okay, we will look into the delay element, into the capacitance element, coupling effect, okay, and do the analysis, so on. And then the DSM interconnect, we continue for another week after you come back from mid-semester break, okay? We continue, and then after that, we will do discussion on power dissipation and low power design, as I mentioned to you all just now. We have to, we have allocated 2 weeks, 2 weeks as well. So it means that is important, okay? Lots of calculation under this section, lots of calculation, okay? But don't worry, the calculation is a standard one. We don't have a triple integration like your calculus or your higher level of mathematics. A power distribution design, okay, chip submodule design, and lastly, chip design methodology. So chip design methodology is actually extension version of VLSI design methodology. Okay, if you want to explore this subject and make it interesting, I suggest you start from this topic. When you start from this topic, you read inside the textbook, though, and then you will have a lot of WH question in your mind. Why and how, what, and so on. So normally, just to share with you all how I study, that's how I study. I always explore the hard thing first, the what we call the complete block, the big picture first. So that when you go down, when you explore it, you have a lot of WH, why, how, and so on in your mind. And when you have that one, you feel it interesting to explore. Okay, when you feel it interesting, and then you can memorize or understand it very, very effectively. That's the idea, just an idea. It's up to you. Any question? Ada soalan? So this is a planning. Yeah, no, okay, thank you. So this is the planning. We will do assignment on week 4. Just a planning. Just a planning. This actually is I collect the assignment, not give you assignment. So maybe I will give it to you maybe next week or week after next week, week 3. I give you assignment and assignment. As I mentioned to you, I think we have the mapping. I think below this. Yeah. So normally assignment, okay, look at the assignment. I give you for PO number 12. Means that I will give you in a group. Okay, G here means that group. Okay, group. So you will do in a group, and then I will give you assignment to do a reading on certain application, certain topic, and then you do a report, or you do your assignment on that one. Okay, maybe it's different group, different topic of assignment. Maybe the assignment on how do we reduce power in our chip. For example, you go online, get a paper, then do a reading, and then summarize it. Okay, and then using your own words. Okay, and then that's actually assignment. So it's contribute 10%, quite high. 10% for assignment number 1 and 10% for assignment number 2. So altogether 20%. This is an element of continuous assignment. Okay, okay, and then lab report 10%. Okay, lab report 10%. Although it's 10% is very important for you, it will help you to understand the subject. Okay, try to make use the lab as much as possible so that it will support you in the learning process. Okay, so this is actually the element of continuous assignment, coursework kamu lah, your coursework. And then we also have tests. 2 questions on test, which cover CO number 1. So I will ask you on sequential circuit design, have your ability to analyze behavior of sequential circuit design. Okay, so KL is knowledge lah, KL is knowledge, bukan Kuala Lumpur, KL is knowledge. I will expect you to have a knowledge on it. That's what I mean by KL. So keep 2 questions, question number 1, question number 2. So this is individual. The total percent is 10%. Okay, and then the final exam, question number 1, number 2, okay, knowledge. Question number 3, number 4, design, maybe non-design, yes, design. Okay, lab, yeah, design. Assignment, lifelong learning, PO number 12. This is PO number 3, okay, and this is PO number 1. Any question? Tak ada. Kalau ada, just stop me lah. So all together become 100%. Okay, final exam 60% as I mentioned, and your continuous assessment 40%. So our final exam will be face-to-face. So please make a necessary arrangement according to the university rule. When you back, make sure that you come back with for the final exam. The lab you will try to do it online, okay, if possible. If not, you need to come back to the university lah. Okay. Last semester or last year exercise we did online, okay, because of the COVID. Okay, it looks okay, but the student need to have extra effort lah, especially when the software being shared across the not only for year 3 but also year 4. Student need to follow the schedule lah, the lab schedule under the what we call timetable. That's why I mentioned, I remind you all to reserve the 4 slots of the timetable. Okay, I think I need to share the timetable as well. Wait, sebelum saya lupa. Timetable, timetable, yeah, this one. This is your timetable. Yeah, clear. So I think same as the final timetable. So we have lab group 1. Okay, MMAD is advanced IC design lab. So we will try to do online first. Okay, so 2:30 to 4:30. So check with your timetable. I think same. Lab group 2. Okay. 3:30 to 5:30, and lab group 3 8 to 10 a.m. in the morning, and lab group 4, I think this is group 4. Okay, 11:30 to 1:30. So lecture is today 3 to 5, and tomorrow. Okay, tomorrow maybe we don't have the lecture, okay, because just week 1. But if you need a lecture, and then just let me know. I will go on it. Okay. All right. So, any question on this? So please make sure you reserve your time, okay? Because the allocation of the group and also the time slot, I cannot, check one by one. So I will do according to this time slot. So you might be allocated for Thursday, for example, maybe allocated for Monday and so on. Okay. All right. Okay, this one, finish. Okay. I think that's all for this one. Don't worry about the mapping here. Okay. Any question? If no question, we shall go to the lecture. Ada 1 jam lagi. You nak take 5 ke? 5 minute break, okay? Okay, so we'll start 5 minutes past 4. So in the meantime, you can go to the lecture note and explore. If you have any question, you can ask me after this. Okay. Any question? Ada soalan tak? No question, we proceed. Assume everyone okay, right? So this is the lecture. So before we start, I encourage everyone to jot down the important notes. Don't rely on the recording because the recording might take some time for me to upload. Okay, and I normally upload at the end of the at the end of the week lah. Okay, it's depending on the drive capability. Okay, so please jot down the important notes so that you can do revision. Okay? You can use a textbook. I noticed someone has already shared in the WhatsApp group. Good. Okay. So actually the ebook subscribed by university. That's why we have access to it. So jot down important information and so that you can refer to the ebooks. Right. So the syllabus already discussed just now. Reference book also discussed. Now we go to introduction to VLSI design. Okay, what is VLSI? Stand for very large scale integration. I believe every one of you already know this word, VLSI design, VLSI. Okay, so we also have ULSI, LSI, and so on. The terms actually depends on the number of transistors. How many transistors inside the chip? Okay. The design or manufacturing of extremely small. So normally when we talk about VLSI, okay, it's actually we referring to extremely small chip, okay, chip yang kecil, extremely small, very small. Even your handphone, your mobile phone, if you explore your mobile phone, you open and you check the processor inside your mobile phone, it's very small, okay. That's actually technology of the VLSI, ULSI, and so on. Okay, a lot of thousands, billions of transistors inside the chip to implement what? Complex function, okay, and complex is comprised of complex circuitry, complex circuits. Okay, the circuits actually implement functions. Okay, if you remember, you learn introduction to IC design. Okay, you learn digital IC design number 1 and number 2. Digital design 1, digital design 1, digital design 2, and also digital IC design. So you know already, especially digital number 2, digital. You know already the Boolean equation, okay, where you from the Boolean equation is actually you can get a circuit. Okay, circuit comprises of PMOS and NMOS transistor. That's actually a circuit. Just imagine one inverter, we need 2 transistors. Just imagine if you have designed a processor. Okay, the processor comprises of an ALU, memory, controller unit. Okay, so that's among the important element inside the processor. So how many transistors inside? Okay, that's why we have complex circuit inside it. Okay, to implement a complex circuit, we need to have a smallest possible circuits. So, smallest possible circuit we can achieve using a smallest possible transistor fabrication technology, nanometer, micrometer, and so on. That's actually the relationship between the semiconductor process technology, okay, to the size of the circuit, okay, size of the transistor, and consequently size of the chip. Okay, so integrated circuit may contain million, as I mentioned to you all, million of transistor, okay, each few micrometer in size, okay. So normally the size of a transistor in micrometer or nanometer, okay. Okay, so what's actually the current process technology fabrication punya process technology, we call process technology. So that can be part of your assignment number 1, for example. You explore what's actually the existing, the current process technology used by the company. Okay, is that still a micrometer or nanometer, or maybe even smaller than that? So what is actually the relationship between the size, the channel length of a transistor, okay, to the size of the chip to be designed? Maybe you explore, you go get a reference book or get a journal, explore and relate to your textbooks, and then come up with your conclusion, okay, for your assignment. That's actually about the assignment. So application wide ranging from for most electronic logic devices. Okay, lots of application actually, right? Not only for mobile phone, they also use for drone technology. You know the microcontroller, Arduino microcontroller, ESP32. You I think you're familiar. ESP32, ESP, other ESP version. Okay, not MCU and so on. So inside the application chip, we have the microcontroller, we have the processor design using a VLSI or ULSI technology. So why VLSI? Okay, so better than discrete component. So I think you know TTL chip. Okay, TTL chip, like maybe I can show. Everyone can see it. So this discrete chip. Okay, if you click on this, these are discrete chip. For AND gate, for example, a NAND gate, sorry. So NAND gate, so you have only 1, 2, 3, 4 only. Okay, the chip is very, not to say very big lah, but big lah, like this one. Okay, so you just imagine how many chips that you need to implement a processor, for example. A lot, because you need to have a lot of NAND gate. Okay, 2 input NAND gates. Normally chip design, we use a lot of 2 input NAND gate. Okay, so to implement it using discrete component like this, your circuit will be complex. It will be bigger, will be so big. Okay, so how do people improve it? They use VLSI technology. Okay, so they integrate it to improve the design. How do they integrate? They integrate using a design-like approach lah. It's not using plug and play lah. They design. Okay, that's actually the role of a design engineer. Design engineer write a code. Okay, normally using Verilog or VHDL. Okay, or even some use C code. Okay, to design that system. Okay, and then they do the what we call logic synthesis, as I discussed you all just now, and then get the equivalent layout comprises of 1,000 or billion of the transistors representing the processor, for example. And integration also improve in terms of course, in terms of area. As I mentioned just now, instead of you combine all the discrete component, you integrate all inside the design. Okay, and the design will become, the chip will become, and of course, when it's smaller, it reduces the power consumption and also higher speed. Okay, easier thing for you to remember to relate between the speed and also the area. Okay. Just imagine yourself in a building. Okay, in a building. So if the building is not is everything inside the building, your cafeteria, your lecture hall, your hostel, is everything in walking distance, it will be faster for you to travel from one place to another. Okay. For example, I will lecture at 3 o'clock, so you can even wake up or get out from your hostel 3 minutes before, maybe 5 minutes before, because of smaller area or walking distance. But if the area is bigger, You cannot access it within 3 or 5 minutes. That's an example of analogy for you to understand. But to answer a specific question regarding VLSI design, especially in the test or exam, don't use that analogy. You use analogy related to the digital design. Okay, this is for you to understand the concept. Okay, lower power dissipation. So as I mentioned to you, these three criteria will be important for this course: speed, power, and also area. Okay, area. Physically smaller is actually referring to area. So integration reduces manufacturing costs. We're not going to explore detail on the cost, but it has direct impact actually to the cost. Okay. No manual assembly, like a discrete component, as I mentioned to you, the TTL chip, like this one. Okay. When I was an undergraduate student, I used this one. During that time, there was no sophisticated software like Synopsys, even Quartus for, I think, is not available yet. Okay. So we do a manual assembly. Okay. Just to do a simple operation, for example, an adder. So we have a discrete chip like this one to implement an adder. Yeah. So now we have the technology, and then we can. That's why you see the chip getting smaller, and then a lot of application can be implemented. Okay. So integrated circuit. So what is IC? Integrated circuit. So as a name, you can see integrated. So it's integrate together. Integrated circuit. So a semiconductor chip. This is the definition. Maybe I can okay, use pen's keyboard. Okay. Okay. So a semiconductor chip is a complex electronic component and their interconnection, which is fabricated. So they fabricate it. What is fabrication? Fabricate is actually a process of actually implementing the physical design into the actual chip. Okay. So we're not going to explore until fabricate for your fabrication, for your course. Your course is until physical design, ready for fabrication actually. Okay. Okay, digital logic is implemented using transistors, as I mentioned to you. So this is example of what is this? What this circuit perform? What is the equivalent function of this one, of this circuit?
Inverter.
And inverter. Okay. So this is actually a logic circuit. If we give 1, it will give you 0. If we give 0, it will give you 1. It looks simple, but it's actually implementing a lot of function. Okay. For example, is used to convert any digital signal, either 1 or 2 equivalent to different value, 0 or 1. So it's being used in a lot of application. So this can be a part of assignment. I can also ask you, okay, explore the application of an inverter in various IC design application. So digital logic is implemented using transistor and in IC containing many gates. Okay, so this is an example. So we have 2 transistors, PMOS and NMOS. Okay, just to implement this one logic gate, which is the inverter. Okay. Right. We have small scale integrated circuit, we call as SSI. Okay, so during that time, only 10 gate or less. For example, logic gates. During that time, chip fabricated for what we call as simple logic operation. As you can see just now, the NAND gate, 2 input NAND gate fabricated in a chip. That is SSI. And then medium scale integrated circuit, MSI. Okay, so the number of gate during that year, that time, 1000 gates. Then we can implement even higher function or higher function of a circuit. Just imagine from logic gate, now we can implement adder or counter inside one single chip. So we able to integrate about 1000 gate inside a chip. And then we have LSI technology, contain up to 10K. So 10K, you can implement a multiplier. And then now VLSI in our course, the number of gates more than 10,000. Okay, and that capability able to implement microprocessor. Okay, microprocessors more than one inside a chip. Okay, that's VLSI. Okay, improvement in manufacturing lead to ever smaller transistor. So it means that the process technology, the PT, PT stands for process technology. Okay, normally micrometer, nanometer process technology. Okay, nanometer. This process technology actually allow for even smaller transistor. Okay, so this is an example of a transistor. Okay, smaller transistor allow more space for a lot more transistor to be included inside a chip. Okay. Remember, to do a fabrication, we have a silicon wafer, right? So this is your wafer. Okay, wafer like this one. Okay, maybe this is your wafer. Okay, to do a fabrication, so maybe this is actually the number of chip that your that a system can be used. Okay, so this one die, we call this one is die. We call this die, DIE. One silicon die can implement, for example, 10,000 bits or a microprocessor. Okay, so if we can reduce the size of the transistor, we might double the number of die available or capable to be produced by from this wave. Okay, right? So that's actually mentioned by this word, allowing more per chip. Okay, more die per chip. Okay, need to remove it. So 10 to the power of 7 gate per chip now possible because of the size is double every 18 months. This is actually the most law. If I think most of you heard about it. Most law. Okay. Right. Variety of logic family, we have TTL, CMOS, ECL, gallium arsenide. Okay, so normally for this subject, we focus on the CMOS. What is CMOS? C stands for complementary. Complementary because we have PMOS and NMOS, so the combination of these two. Metal oxide semiconductor. So this is actually the comparison. This is for your information. Okay, why they choose CMOS, why they choose TTL and so on. So in terms of propagation delay, okay, gallium arsenide is the fastest. The smaller, delay means that the fastest lah. Okay. So in terms of power dissipation per gate, It's about 5 microwatt, sorry. Okay, 5 microwatt. For the case of gallium arsenide, is in milliwatt. The more compared to the CMOS. Okay, but the best one is the best one is CMOS, sorry. This is micro. And then in terms of fan out to other chips, okay, it's excellent. So its ability to drive other chip lah, fan out, okay. Okay, and so on. You may read on your own. Okay, and in terms of cost, okay, 30 cent, 31 cent. Okay, and the rest is higher cost lah. Okay, this one and also this one is 38. So that's why we choose the CMOS. Mostly that's why people choose CMOS. Okay, and that's why CMOS is still becoming the what we call reliable. This is Moore's law. Okay, you can also explore Moore's law for the year of 2022. So this can also be part of your assignment. For example, assignment number 1. What happened in Moore's law? Is that still reliable? Is still usable? Number of transistor double every 18 months, or no more? Right. So first proposed in 1960, CMOS. Okay, it was seriously considered, but you can read on your own this one. It's a dominant technology, okay, and use both PMOS and NMOS as I mentioned. So you also learn the PMOS and NMOS under the introduction to IC design, I believe. Okay, and also you learn on the fabrication process for the PMOS, NMOS, PWell, and well, right? Using we're not going to cover this one for this course now. Okay, and here is the advantages of the PMOS: fast, cheap, and low power transistor. I think if you go back here, it's actually fairly with this one. Okay, faster. Okay, lower cost. Okay, and low power consumption. Okay, or low power dissipation. Okay, you can relate which one with the diagram that we have on the previous two slides. Slide number 13. Yeah, number 12. Okay. Right. We also have different variation of what we call as like a hybrid. We have a bipolar and CMOS. Okay. We take the advantage of bipolar, okay, which is higher gain, higher in gain, better noise characteristic, better high frequency, and then we combine with the previous dimension CMOS advantage, fast, cheap, low power, and so on, and then it becomes by CMOS. Non-deficiency of MOS technology is limited, okay, due to limited current sourcing and sinking abilities of PMOS and NMOS transistors. So that's why they introduced a bi-CMOS combination of bipolar characteristic and also. So, okay, don't worry about this one. So maybe we can give another assignment topic. Okay, assignment number 1. So for the other group to explore bi-CMOS and CMOS. Are they still reliable? Which one is the best, bi-CMOS or CMOS? We also have another other type of application, which is ECL, electrically, forgot the full name. So critically high speed parts. Okay. So what are ASICs? Just now we learned about VLSI. VLSI, as we can what we call summarize, VLSI is more to the number of transistors. Okay, how many number of transistors can we integrate inside the chip? Okay, we already know 10K or 10,000 transistors per chip. That's actually roughly more than 10K if I'm not mistaken. More than 10K bits per chip. Okay, what are ASICs? So any IC other than general purpose IC which contain the functionality of thousands of gates usually called ASIC. The the best or the easiest way to understand, you see the word A here, A and S. So it's application specific. IC that is designed for application specific, okay, specific to any application that we call as ASIC. Okay, it's kind of integrated circuit, but designed for specific application. Okay, ASIC are designed to fit certain application. Yeah. Okay, ASIC is digital or mixed signal designed to meet specifications set by the specific project. Okay, but in this course we focus on digital and not a mixed signal. Okay. Any question before we proceed?
No, doctor.
Mm. Mm. Okay. Oh, finish. BSI design methodology. So this actually to be covered in next week. It's okay. So I will share to you all the textbook lah put. Wait, I will get the ebook so that everyone have the idea lah on the ebook. Okay. Alright. Any question? No question, huh? Semua faham, huh? Okay, good. Okay, this is actually the textbooks now. So 867 pages. Don't worry about this. Just what we call, we will not cover all. So for example, this is really the one that I mentioned to you. If you want to explore what we call this subject and make it very interesting, you can start at the very end of the chapter. Okay, you can see the process. Okay, here is actually the level of abstraction. Okay, you look at the angle of here. You see, we already discussed this one. You look at the lower levels, the inner we go, okay, the inner we go, the lower the level, okay. For example, we go to the structural domain here, okay. So processor, SOC, okay, this is actually the higher level in terms of the structure of the digital circuits, okay, digital system. Processor, SOC, and then hardware modules, ALU register, this is actually the RTL level, okay. And then we also have gates level, okay, and then transistor level, okay. and we can even go to a lower level, okay. So, but this is actually the fundamental for you to understand. And we can also look to at different other level, okay, like this one. We have system level, algorithm level, okay. So the higher level, which is a system level, okay, and then going lower, algorithm level, register transfer level, logic level, and so on. This is what we call as Y chart. Y chart. Okay, I think most of you are familiar with it. That's what I mentioned to you all. Okay, the viability of an IC is large, blah, blah, you can read on your own. A good VLSI design system should provide a consistent description of three domain, behavior, structure, and so on. And then normally performance, as I mentioned to you, we will look into this one, speed, power, and area normally, okay. This is the area, size of the die. Okay, time to design and so on. But subject focus on the three. Even the lab, you will look at the three elements. You can read this, okay, have an idea on what's actually the digital IT design or VLSI design or how it works. This is actually no need to worry about all of this, just to get an idea, okay. We go to, I think, yeah, so to get an idea, this is actually FPGA, okay, FPGA. No, we're not using FPGA in our design, in our subject, sorry. Just for your information. And then you can see how just recall back what you learned, okay, full custom and so on. Just read, not detail, okay. This may be good for you to understand between the FPGA and also the VLSI design or SOC design. So FPGA, normally we download our design into the FPGA chip. Okay, different type of FPGA. For example, Altera got Cyclone FPGA, and Xilinx got different version of FPGA. Okay, so normally for our VLSI design, this is actually the design flow. Okay, start from our course will cover the back end, as I mentioned to you just now. Okay, structural specification, okay, physical synthesis, okay, physical specification, and then to CMOS fabrication. But for CMOS fabrication, we're not going to fabricate. We stop before the fabrication. Okay, they call GDS2 file. Okay, so the front end is actually covered in digital IC design, whereby you use the quarters tool to do the behavioral modeling. Okay, they call here behavioral or functional specification or modeling, and then you do the synthesis. Okay, before synthesis, normally we do the simulation. Okay, RTL simulation. That's actually the flow. This also explained to you about RTL and so on, and also ASIC as well. So if you like to explore, you may start from section 14.4, design flow. Lots of information available here until the physical synthesis. This is actually more detail for RTL synthesis flow. Okay, what happened, okay, and so on. So for in terms of library, we'll be using TSMC library, okay, TSMC. Okay. Also, I think explained to you about logic synthesis, placement, the process I explained to you. So you can start from that section until what is floor planning, what is routing, what is parasitic extraction. You may read it. Okay, and then it will give you detail. Okay, operation. What is clock tree, routing, power analysis. Okay, and stop before mixed signal. Mixed signal, I think we not cover in our syllabus. It's a lot. In design economic also no need. Here that part only. The section 14.4, I think. Recurring cost. No need lah. No need. Okay, this one is the process technology. So the fact that they try, don't worry, no need to read this one. Okay. I think that section only lah. Okay, you explore. Okay, to get the view of the VLSI design. And I think Habis, finish testing and debugging is not part of our course lah. This will be covered under design for testability. That subject I think to be covered by Dr. Azizi. Okay, very interesting lah. Electronic program flow very interesting. You will have all the flow lah. Okay, okay. I think that's all. Okay, we will take a group photo. Boleh? Everyone ready for attendance?
Okay, Doctor.
Okay, to get ready, I will call for a group photo. We take photo together. How many of you didn't see my face? Not recognize me? Boleh raise up your hand. Kalau ramai, maybe I will on my camera lah. I stop the recording first.